What is acetylcholine? Acetylcholine, often abbreviated as ACH, was the first neurotransmitter ever discovered, and it remains one of the most essential in the human nervous system. In the central nervous system, acetylcholine plays a vital role in learning, attention, and memory formation by modulating activity in key brain regions such as the cortex and hippocampus. In the peripheral nervous system, ACH functions as a critical messenger at neuromuscular junctions, where it binds to receptors on muscle fibers and directly triggers contraction. Due to its presence in both voluntary and involuntary control systems, acetylcholine is often described as a neurotransmitter that bridges mind and motion. Acetylcholine receptors, muscarinic and nicotinic acetylcholine, exerts its effects through two distinct classes of receptors, muscarinic and nicotinic. Muscarinic receptors are G-protein-coupled receptors primarily found in the brain and internal organs. They mediate slower modulatory responses that are important for regulating functions like heart rate, glandular secretion, and cognition. In contrast, nicotinic receptors are ligand-gated ion channels that respond quickly to ACH binding by opening up and allowing sodium ions to flow into the neuron. This results in rapid depolarization and signal transmission, especially at neuromuscular junctions. Together, these two receptor types allow acetylcholine to fine-tune processes ranging from instant muscle control to long-term memory encoding. Dopamine-acetylcholine balance in the basal ganglia. In the basal ganglia, a network of nuclei responsible for coordinating movement, a delicate balance exists between dopamine and acetylcholine. Dopamine activates the direct pathway, which facilitates movement, while acetylcholine activates the indirect pathway, which inhibits movement. This opposing interplay ensures that movement is precise, purposeful, and well-timed. If either neurotransmitter becomes dominant or deficient, the balance is disrupted and motor dysfunctions arise. This dynamic is central to understanding motor disorders like Parkinson's disease, where the reduction in dopamine tips the scale toward excessive cholinergic inhibition. Parkinson's disease, loss of dopaminergic control. Parkinson's disease develops when dopaminergic neurons in the substantia nigra pars compacta degenerate. These neurons normally release dopamine into the striatum, helping activate the direct pathway and keeping acetylcholine's inhibitory effect in check. As dopamine levels fall, acetylcholine becomes functionally overactive, intensifying activation of the indirect pathway. This results in excessive inhibition of movement, leading to the hallmark motor symptoms of Parkinson's disease: tremors, muscle rigidity, bradykinesia, and postural instability. At its core, the condition reflects a neurochemical imbalance where the brain's movement circuits are dominated by unchecked cholinergic signals. Using selective muscarinic antagonists. To reduce the side effects of traditional anticholinergic therapy, scientists are now developing more selective drugs. Instead of blocking all muscarinic receptors, these drugs target specific subtypes, like the M1 receptor. Since M1 receptors are involved in motor control but less in cognition, selectively inhibiting them may improve symptoms like tremor and rigidity without causing memory problems or confusion. 2. Gene therapy. Gene therapy offers a groundbreaking approach to treating Parkinson's disease at its root. Using viral vectors, researchers can deliver genes that increase dopamine synthesis or suppress overactive acetylcholine-producing neurons. By targeting the source of neurotransmitter imbalance, gene therapy may restore the natural communication within the basal ganglia and offer long-lasting improvement. Off-drug strategy. Beyond medications, the future of Parkinson's care includes strategies that retrain the brain itself. Regular aerobic exercise, physical therapy, and even neurofeedback can enhance neuroplasticity, the brain's ability to rewire itself. These approaches may help restore balance between acetylcholine and dopamine over time, allowing patients to regain better motor function naturally.